Hello, everyone, and welcome to lecture 19 of GPU computing. Today, we're going to continue talking about graph processing. So last time we started, and today's lecture is just a continuation of last time's lecture. So last time we started talking about graph processing. We said that we represent graphs are represented usually as adjacency matrices, which are sparse matrices. So we can represent graphs using the same formats that we use to represent sparse matrices. So this was an example of a COO representation of the graph, where we basically have a list of edges, and for each edge we have the source vertex and the destination vertex of the edge. And then we also saw a CSR or CSC representation of the graph, where we have for each vertex, the source pointer is a pointer to the list of outgoing edges for which that vertex is a source, and that points into this array that has the destination vertices of the edges. And we said that we're focusing on unweighted graphs, and that's why we just have a bunch of ones, so we don't store the values with this representation like we did with sparse matrices. But if we had an unweighted graph, then we would have had a third array in each of these representations with the weights. And we also said that we're focusing on symmetric graphs, so CSR and CST are equivalent. And this was useful when we did the direction optimized version, where we were able to use the same representation of the graph for both directions. We said that there are different approaches to parallelizing graph processing: vertex-centric, where we assign a thread for every vertex to do something for a vertex, or edge-centric, where we assign a thread to do something for each edge. And then obviously each one of these comes with its own preferred format. So if for vertex-centric, we want to access the edges of a vertex, so CSR is useful, whereas for edge-centric, we want to access the endpoints of an edge, so COO is useful. The example that we looked at was breadth-first search, and the formulation of breadth-first search we looked at was where we wanted to go through all of the vertices in the graph and label them based on their frontier number, which is basically their distance from some source vertex that we selected. And we looked at different implementations of BFS. We saw a top-down implementation where on each iteration, the thread is assigned to a vertex. It checks if that vertex is in the current level, and if it is, it puts its neighbor in the next level if its neighbors are unvisited. We looked at the bottom-up vertex-centric approach, where threads were assigned also to vertices, but this time the thread would check if its own vertex was not visited. It would check if any of its neighbors are in the previous level, and if it is, if any of them are, it would put the vertex in the current level. And we saw how each of these was good at in a different situation. So we looked at the direction optimized version that did top down initially and then bottom up later on. And we also saw an edge-centric approach where every thread essentially owned an edge. So the thread was only responsible for checking if one source vertex is, if the source vertex of the edge was in a previous level, and if it is, it would add the destination vertex to the next level. We also saw the data set implications of the data set implications on performance, and we saw how the vertex-centric bottom-up and the edge-centric approaches are better on high-degree graphs because they're better at dealing with load imbalance, whereas the vertex-centric top-down approach was actually better for low-degree graphs. And we ended by observing that there's actually a similarity between BFS and SPMV. And here, the way that we kind of implemented SPMV before with CSR was similar to how we did the vertex-centric bottom-up BFS. And in fact, the other variations of BFS that we looked at also correspond to other ways of performing SPMV. And we said that in general, a lot of graph problems can be formulated as linear algebra problems using the adjacency matrix of the graph. And with a few tweaks, we can actually formulate BFS exactly like SPMV. And the advantage of that is that we can leverage libraries for sparse linear algebra to also implement graph algorithms. The disadvantage, however, is that formulating a graph problem used as a linear algebra problem is not always the most efficient way to solve that graph problem. And we ended with talking about redundant work. We said that the approaches so far were checking every vertex or edge on every iteration to see whether they're relevant for that iteration. And that meant that a lot of threads sometimes would just get launched, and then they would figure out that their vertex or edge were not relevant, so they simply wouldn't do anything. So that would have been a waste of threads. So the strengths of this approach is that it's easy to implement, highly parallel, and we don't synchronize across threads. However, the weakness is what we said, a lot of unnecessary work. So what we said we're going to cover today is another approach where we avoid launching threads for irrelevant vertices or edges. We just launch threads for the vertices that are relevant to the computation, but this requires more synchronization, as we will see today. So today, we're going to continue talking about graph processing. Before I begin, does anybody have any questions about last time's material? It's important that you understood what we covered last time because we will build on it today. So anybody have any questions about what we covered?
Yes, doctor. What would change if the graph was not symmetric? The edges.
So I said I would talk about that. And I think maybe I did forget. Now, so what would change when the graph was not symmetric is when we did the top-down approach, every thread was looping over every thread was going over its neighbors that are reachable through the outgoing edges. Whereas when we do the bottom-up approach, we are looking at our neighbors through our incoming edges. Okay. So when the graph is not symmetric, so when the graph is symmetric, the incoming edges and the outgoing edges are the same. Okay, so our CSR representation is the same as our CST representation. When the graph is not symmetric, then the incoming edges and the outgoing edges are different. So in this case, the top-down approach wants to look at the neighbors that it can reach. So it looks at the outgoing edges. So in this case, it would need all the edges that go from itself to its neighbors, and that would correspond to the CSR representation of the graph. Whereas in the bottom-up approach, we are looking at all the neighbors that can reach us, not all the neighbors that we can reach. So all the neighbors that we can reach us are the incoming edges. So I want to look at all the sources that can reach me as a destination, and that would correspond to the CST representation of the graph. Okay, so the top-down approach requires a CSR representation of the graph. The bottom-up approach requires a CST representation of the graph. Okay, and because of that, because the graph was symmetric, we were able to use the same representation for both the bottom-up and the top-down. So when we came to the direction-optimized approach, it was enough to just use the same graph in both cases. Okay, is that clear?
Yeah, so for direction optimized, we would have to use both the CSR and CSV, right? If it was not symmetric.
So for the direction optimized, yes, you would have had to keep around both a CSR and a CST, so that when you did the top-down approach and wanted to loop over your outgoing edges, you would have your CSR, and then when you switch to the bottom-up approach and you want to go over your incoming edges, you would have to use the CST.
Okay.
It also depends on how you interpret the matrix. If you interpret the matrix as the rows being the source vertex and the columns being the destination vertex, or if you interpret the matrix in its transposed form. Okay. The point being is that one of them requires CSR and the other one requires CS. Okay.
Okay, thank you.
Yeah, you're welcome. I'm saying that because when you do the linear algebraic formulation where you formulate where you formulate the BFS as SPMV, you actually treat the rows as the destination vertices and the columns as the source vertices. Okay, so it would be the opposite of what I said. But what we looked at this time, we were treating the rows as the source vertices. Okay. All right. So let's. Any other questions about last time's material? Okay, so then let's proceed. So today we're going to talk about how we can reduce redundancy. So if you recall, the approaches that we discussed so far, they check every vertex or edge in every iteration, and that results in unnecessary work. So the alternative for doing that, for reducing redundancy, is to do the following. Our objective is to only check the vertices that are part of the previous level. We don't want to check all vertices at reiteration. So the approach that we're going to follow is that on each level, what we will do is we will place the vertices that were visited on that level in a queue. And then on the next level, what's going to happen is we're going to only process the vertices that are in that queue. Okay? So the vertices will be queued on each level, and these vertices form the level's frontier. So we call this a frontier-based approach because what happens is on every level we're going to construct a frontier, and on the next level we're only going to visit the vertice. We're only going to process the vertices that are in that frontier. Okay. Now the advantage of this is that we reduce redundancy, but what's the disadvantage of doing this?
Like we have to use atomic operations or contention on the same queue.
Right, so we have a shared queue, right? All the threads are trying to add to a queue, so we have synchronization across threads to add to a shared queue. So this is going to be the overhead, but the benefit is that we are avoiding redundancy. So you can imagine that in some cases this might be better, in other cases it may not be. But hopefully today we're going to look at an example where this will hopefully improve our performance. Okay. So let me just illustrate what I mean by this approach before we go to implement it. What we have is we're going to start at level 0, and when we go from level 0 to level 1, we're going to initialize we're going to have this queue that's going to represent our frontier. And here, this queue, which is our previous frontier, is going to be initialized to the source node. Now, when we call the first kernel is going to process all the vertices in level 0 to generate the vertices in level 1. So now here, since I only have one vertex in level 0, I only need one thread to process this vertex, right? So as opposed to launching a thread for every vertex, and then all these threads figuring out that they're not relevant for this iteration, I'm only going to launch one thread for this vertex, and then this thread is going to construct the next frontier, okay, by visiting all of its neighbors. Okay, so this is the vertex-centric top-down frontier-based approach. Now, on the next iteration, the frontier now becomes the previous frontier, and what we want to do is we want to construct the frontier for level 2. So we're going to launch a thread for every vertex in the previous frontier. So this time we're going to have 4 threads for these 4 vertices. Each of these vertices are going to go through their neighbors, figure out which neighbors are not visited, and they're going to together enqueue their neighbors in the next frontier. So we're going to have these vertices that are neighbors of the level 1 vertices in the next frontier. And then same thing happens in the next iteration. This one becomes the previous frontier, and we have a thread for each one of the vertices in the previous frontier, and these threads will visit their neighbors, and they will enqueue any unvisited neighbors in the next frontier. And then on the next iteration, this one becomes the previous frontier, and we're going to have a thread for each one of these vertices that are in the previous frontier, but none of them are going to find any visited neighbors, so our next frontier is going to be empty, and this is how we know that we are done. And everything else that we did not reach is going to be unreachable. All right, clear how this works? Okay, well then let's go and implement this. I'm going to switch to the code terminal. First, let me remind you how the vertex-centric top-down approach performed. So I'm going to, or it's already compiled. So I'm going to run BFS on, remember the top-down is best on road graphs. I'm going to focus on the road graphs for this lecture. So here, when we did the top-down approach on the road graph, we got around 6 milliseconds. But now let's go and take a look at how we would perform if we use the frontier-based approach. So I'm going to open the code over here. So I've already set up the host code. The CSR graph is the same, so we have we allocate memory for the graph and we copy it, but we also initialize a previous frontier and a current frontier. And by the way, we're only going to initialize 2 buffers, and then we're going to use double buffering. So on one iteration, the previous frontier is, we have a previous frontier and a current frontier. On the next iteration, we're going to swap them. So the current frontier, so one buffer becomes the current frontier, and then we use the other buffer for the previous frontier. Sorry, one buffer becomes the one that was for the current frontier becomes the previous frontier, and then we'll use the other buffer for the current frontier. So here we loop over this, and notice how we're going to call it the BFS kernel, and then every iteration we swap the buffers. This is how the double buffering is happening. We swap the previous and the current buffer every time. Okay, so now let's go back up and implement the kernel. The kernel takes the graph, it takes the level, and then but it also takes the graph, it takes the level, but it also takes the number of. Let me grab the code so you guys can see what's happening. Okay, so we have the graph, we have the level. This is the level of each vertex in the graph. We have an array that represents the previous, that's going to contain the vertices of the previous frontier. This is going to be initialized to just the source vertex. We're going to have an array that's going to be where we're going to put the vertices of the current frontier. We're going to have the number of vertices in the previous frontier. So when we access this previous frontier array, this one tells us how many vertices there are there. We have the number of vertices in the current frontier. This one's going to be initialized to 0, and when we add stuff to the current frontier, we're going to use this counter to figure out where we're going to add. And of course, we're going to have the current level, which tells us the level that we are currently in. Okay, so let's get started. So what we want to do initially is we want to assign a thread for every vertex in the previous frontier. So the thread index is going to be the index into the previous frontier that we're going to use. So we're going to start off by figuring out our global thread index. We're going to have unsigned int I is equal to blockindex.x times blockdiv.x plus threadindex.x. Okay, and then we need to do a boundary checks because we need to make sure. Remember, we're going to use this to index the previous frontier, so we're going to need to make sure that it's within bounds. So what do we compare it to? We're going to compare it to the number of vertices in the previous frontier, which is now the previous frontier over here. So this is our boundary check. Okay, now what we want to do is we have the index of the previous frontier. We want to obtain the index of the vertex itself. So we're going to load the index of the vertex from the previous frontier. So if we assign int vertex is equal to previous frontier of I. So now the thread has the vertex that it's responsible. Once the thread has the vertex that it's responsible for, what it wants to do is it wants to loop over its outgoing edges. How does it know where its outgoing edges start? Well, remember, this is a CSR graph, so it's going to be just like what we did before. We're going to loop over from the source pointers of vertex to source pointers of vertex plus 1. So we're going to write for unsigned int edge is equal to CSR graph dot source pointers of vertex. Edge is less than CSR graph dot source pointers of vertex plus 1, and then plus edge. Okay, and now what we want to do is we want to find the neighbor at the index of the neighbor at the destination of this edge. So we're going to write unsigned int, unsigned int neighbor is equal to, again, we're going to look at the destination of the edge. So we're going to write CSR graph dot destination of edge. Okay. All right, now that we have the neighbor, what are we trying to do? Well, what we want to do is we want to check if our neighbor is visited. If it's visited, we're not going to do anything. If the neighbor is not visited, then what we want to do is we want to add the neighbor to the next frontier. Okay, or what I'm calling is the current frontier. Okay, so what I will do is I want to check if the level of the neighbor is equal to uint max, which means the neighbor is not visited because it hasn't been assigned a level yet. Okay, if the neighbor is not visited, then what we want to do is we want to visit the neighbor. So we're going to assign the level of the neighbor to be uint max. Okay, and then what we want to do is we want to add the neighbor, right? So we found an unvisited neighbor. So we want to add the neighbor to the next frontier, or in the code I'm calling it the current frontier. Okay. So how do I add? Well, num frontier tells me how many vertices are currently in the current frontier. So I want to increment this. Okay. So I'm going to get the I'm going to increment this. So first of all, this is going to be the number of vertices in the current frontier. So I'm going to write unsigned int so when I load from the current frontier, okay, this tells me how many vertices are in the current frontier. So if I want to add something to it, this is going to be also the index of the new element that I'm going to add. Okay, and then I'm going to increment, okay, the number of vertices in the current frontier. Okay, so I get the old value of the number of vertices in the current frontier. I increment it, and then what I will do is I will add the neighbor to the current frontier at this index. So I'm gonna write current frontier of current frontier index is equal to neighbor. Okay, I look over my neighbors. I figure out the index of my neighbor. I check if my neighbor is not visited. If it's not visited, I visit it. Oh, oops, I made a mistake here. This should have been current level. Okay. Okay. I check if my neighbor is visited. If my neighbor is not visited, I visit it by marking it as being part of the current level, and then I increment the index of the current frontier. Okay. And I add my neighbor. I add my neighbor to the current frontier at the index that I got. Okay. So that's logically what we do, but we have some problems here. What's the problem?
I think we have a race condition.
Right, where we do have a race condition. Where do we have a race condition?
In pushing to the current frontier.
Right, so here when if I have multiple threads that read from the current frontier at the same time and they go incremented, I will have a race condition when adding to the current frontier. Okay, so how do I, let me kind of write this in a better way. So what I want to do is I want to get the old value of the current frontier, and then I want to do a post increment. So post increment gets the old value and then increments the value. So I want to get the old value of the current frontier, and then I want to increment it after I get it. So how can I do this, right? In a way where I don't have race condition.
Atomic add.
Right, atomic add, exactly. So instead of doing it this way, what I'm going to do is I'm going to write atomic add num current frontier 1. Okay, so I'm going to atomically add to num 1 to num current frontier, and I will remember when I do atomic add, it's going to atomically add 1 to this, and it's going to give me the old value. So the old value is where I want to put my my neighbor, and that so I take the old value and I put that in current frontier index. Okay, so now I've solved the race condition for when adding to the current frontier. Is this clear? Any questions about this? Clear to everyone? Okay. I have another race condition. Where is it? What happens if multiple threads in the previous frontier have the same neighbor?
They're gonna add it twice to the queue if they read
Right.
it.
If we're unlucky, right? If we're unlucky, both of these threads will compare and find the neighbor is unvisited. So both of them will mark it as visited in the current level. You know, if we're lucky, one thread will mark it and the other thread will read the updated value. But if we're unlucky, both of them will find it unvisited. Both of them will mark it, and then both of them will add it to the current frontier. So I'm going to have the neighbor added to the current frontier multiple times. That's a problem, because that means on the next iteration, I'm going to process that neighbor multiple times. You can imagine how this can explode exponentially. So how can we avoid having the thread? How can we ensure that only one thread sees the neighbor as unvisited and all the others see it as visited? We're going to need another atomic operation, but this time it's not an atomic add. What does this operation have to do?
It's kind of like a mutex lock.
But we don't want to do a mutex, so we want to just have an atomic operation. But we'll see the atomic operation that we're going to use, but what does it need to do, this atomic operation?
To make
It's like
sure it's a read.
assignment. It has to do assignment.
It has to do assignment, but it has to do assignment. It has to do a conditional assignment, right?
Yes.
I know what is it. Is it
What is
compare and
it?
swap?
Right, compare and swap. Why is it compare and swap?
So we want to make sure that only one thread sees that it's uint max, and it will compare it to uint max. If it is, then it will swap it with the current level, and no other thread will enter the if statement.
Right, exactly. So the atomic operation we're going to use is called compare and swap. And what compare and swap does is that it compares some value to another value, and if that value is equivalent to another value, it replaces it with another value. Not the so if that value is equivalent to some other value, it's going to replace it with not the other value it compared it to, because obviously that wouldn't be doing anything. But it's going to compare it with yet another value. Okay. So what we want to do here is we want to compare level neighbor to uint max. If level neighbor is uint max, we want to replace it with current level. Okay, but we only want one thread to do that. So if one thread succeeds to find C uint max and replace it with current level, we want any other thread to see current level, not to see uint max. Okay, and that's why it's an atomic operation, because we need to atomically compare and swap. Here the idea is we're comparing and then we're swapping. But the problem is that I could have multiple threads compare and then multiple threads swap. But I want to prevent that. I want to have each thread compare and then swap without there being another thread comparing before this thread. So what we will do is we're going to use atomic compare and swap. So let me get rid of all of this. Okay, so I'm going to do atomic compare and swap. The address, the address of what I'm comparing to and swapping is level of neighbor. I want to compare it to uint max. Okay, and if level of neighbor is equal to uint max, I want to swap it with current level. Okay, and then when do I enter this loop? I enter this loop if the old value of level of neighbor was uint max, right? So remember, an atomic add returns the old value. Similarly, atomic compare and swap is going to return the old value. So when I try to compare and swap with level of neighbor, if level of neighbor was uint max, I'm going to swap it with current level, okay? And I'm going to return the old value, which is uint max. If level of neighbor was not current max, I'm not going to do any swap, but I will return whatever that its old value was. So the only case I want to enter here is if I succeed to do the compare and swap, and that means the only case I will enter is if the old value of level of neighbor was indeed uint max. So here I will have equals uint max. Is this clear? Any questions about this compare and swap? So again, what this will do is compare level of neighbor to uint max. It's basically see if the level of the neighbor is visited. If it is uint max, that means it's not visited. It will set it to current level, and then only one of these threads will succeed to do this, and that thread that will succeed will read the old value of level of neighbor as being uint max. So it will pass this if, and it will go into this go inside here and add to the queue. Okay, so now we've solved our race conditions. Let's go and see how this code performs. So I'm going to compile, and I'm going to run the code. And remember, our old version, which was the one that didn't use the frontier, that had the redundancy, it took 66 milliseconds. So now I'm going to run this, and we actually get 14.8 milliseconds. So we've made a substantial improvement because we reduced the redundancy. All right. Clear to everyone? Any questions? Okay. So then this here is the code that we wrote. And then just as a review, when we were enqueuing to the frontier, all these threads were trying to update a counter that pointed to the head of the queue. So if you had a race condition on the head of the queue, what would end up happening is that multiple threads will write to the same location in the queue. So to solve the race condition, what we did is we had used atomic operations so that only one thread can increment this a counter at a time, and that way we don't have any race conditions when adding to the. Okay, so great. We implemented this optimization, got some good performance. Any optimizations that we can do? Think about what's going on here. Any optimizations we can perform? I have all these threads that are contending on this counter and doing an atomic operation. So if all these threads are atomically incrementing this counter, these operations will get serialized, right? These threads are contending on this atomic operation. So how did we deal with contention of atomic operations before?
Privatization.
Privatization, yes. So can we apply privatization here somehow?
You would have to merge the queues somehow. The queues, like the private queues.
Right, but the idea is that we would need to have private queues, each one with its own counter, right? And then we can have each thread block maybe add to its own private queue. And then what we can do is we can merge all these queues. You're absolutely right.
But how do we go about avoiding duplicates, kind of like what we had now?
Avoiding duplicates did not have to do with the part where we were enqueuing. Avoiding duplicates had to do with the part where we were visiting. So we would still use compare and swap when we visit, right? We're not privatizing whatever compare and swap is hitting. Or compare and swap is hitting the levels. Okay, we're not going to privatize the levels because then that beats the whole purpose of using compare and swap to avoid duplication. What we want to privatize is the target of the atomic operation that's doing the enqueuing. Okay. So queue privatization. As we saw, all threads are atomically incrementing the same global counter to insert elements into the queue. And what this means is that we have high latency because of the global memory access, and we have serialization due to high contention. So the optimization that we can apply is privatization, where we have each thread block maintain a private queue, and then it can commit entries to a global queue upon completion. So here, we're going to have each thread block have its own private queue. The threads in the thread block, we can put this queue in shared memory, by the way, to reduce the latency. We can even put the counter for this queue in shared memory so that the atomics the threads in each thread block are going to contend on this counter, but it's going to be in shared memory. And then when each thread block finishes creating or filling up its own queue, what we will do after that is we will have the thread blocks. Each thread block can do one atomic operation on the global one to allocate space for its values, and then it can write its values out to the global queue. By the way, this not only gives us this privatization not only allows us to save on the atomic operation contention, but also now when we're writing this local queue to the global queue, what you can see is our writes will actually be coalesced because we can have each thread write one of the elements of the local queue to the global queue. Okay, any questions about this?
Professor, I didn't understand why there are no duplicates. I mean, what if some node is the neighbor of several nodes and like they share, I mean, they don't have the same private queue. Then that node that's a common neighbor will be in two different local queues, and then it will be twice in the global queue.
No, because I never the way I prevent I never add things redundantly to the global queue, right? So I wouldn't add them to the local queue. The way I'm preventing redundancy in adding to the queue is when I visit, I'm using a compare and swap to visit, so that only one thread will succeed to visit an unvisited neighbor.
Ah, right, I see. Okay. Yeah, thank you.
It's not the queue that takes care of removing the redundancy. It's the visit operation. Yeah, clear?
Professor?
Thank you.
Yes, you're welcome. Yes, question?
Yes, sorry. For to know where each block should write its own queue, is there a scan in between?
So that's a good question. We don't need to have a scan. And the reason we don't need to have a scan, it's different from radix sort. So with radix sort, when we were having all the different threads write their buckets to the global location, we needed a scan because we needed to preserve the order. But here we actually don't need a scan, and the reason is that it's okay if these threads write it's okay if I write this segment here and then this segment later. It doesn't change my correctness. So because I don't need to preserve the order, I don't care about the order in which these segments will be written, these local queues will be written to the global queue. I actually don't need a scan. It's fine if each thread block, whenever it's done, just does an atomic operation, allocate space in the queue and adds to the queue. So maybe this image is a little bit misleading because I'm having the local queues being written in order to the global queues, but they don't have to be. I could have written this one at the beginning, I could have written this one at the end, etc. Clear?
I see. Thank you.
Yep, good question. Okay, so then let's go and implement this optimization. Okay, I'm going to go back to my code. So now what I want to do is I want to create local queues for each block, and I'm going to create these local queues in shared memory. And I also need a counter that tracks where I am in these local queues. Okay, so I'm going to start. So before I do any of this, okay, I'm going to start by creating a local shared memory. Okay, so I'm going to write shared unsigned int. I'm going to call it current frontier underscore s, the shared memory private version of the current frontier. Okay, I'm going to give it a size. Okay, I can let me see what would be a good size. So if I'm using 256 threads per block, so I want to have 8 blocks on the ascent, and if I have around 96 kilobytes of shared memory, then if I want to have 96 kilobytes of shared memory, and I want to have 8 blocks, so each block is going to be able to get 12 kilobytes, and over here an unsigned int is 4 bytes, so I'm going to have 3,000 versus most. Let's say our local queue size is 2048. Okay, so I'm going to write define local queue size is 2048. Okay, and here my local queue size will be 2040. Okay, and what I also want to do is I need a counter all these threads that are in the same block, they need to contend on the same count. They need to increment the same counter to add to this queue. So I'm also going to need a counter to be in shared memory. So I'm going to have shared unsigned int. I'm going to call it num. Oh, yeah, let me wrap. So here I had current frontier, num current frontier. So I'm going to call it num current frontier underscore s. Okay. And now before I start, I need to initialize this to 0, right? So how do I initialize this to 0? Can I just do this?
If thread ID is 0, then this. And
Right.
block
I don't want all the threads to be initializing it to 0. It's completely unnecessary. It's fine if just one thread does the initialization. Okay, so I can write if thread index.x is equal to 0, then I can initialize this to 0. Okay, and of course, what do I need to do after that?
You have to sync.
Right, I need to sync threads because I need to make sure that none of the threads start executing this code at the bottom before I'm done initializing this to 0. So I'm going to sync threads. Okay, great. So now what I've done is I've created this local queue in shared memory, and this local queue is going to be I have this counter that tells me the beginning of the local queue, and I'm going to initialize this counter to 0. Now what I'm going to do is I'm going to go ahead and start executing my code here. So every thread picked up a vertex in the current frontier, goes through the vertices outgoing edges, finds the neighbor, and now what I want to do is I want to add. I want to check if the neighbor is visited, so I'm still going to do this over here. But now, rather than adding to the global current frontier, I want to add to the local one. Okay, so this is the part of the code that's going to change. I'm going to get rid of this. Okay, and now what I want to do is I'm going to add to the local current frontier. How do I do that? Well, I'm going to atomically increment this number. Okay, get the old value and use that to add to the current frontier. Okay, so I'm going to write unsigned int current frontier index. I'm going to put underscore s here. This is going to be the index into the current frontier at which I want to put the neighbor, is equal to, I want to atomically increment to get the value. I'm going to write atomic at num current frontier underscore s and 1. Okay, oops, I need this is an integer. It's not a pointer to an integer. It's not like this one. So I actually do need to have an ampersand here. Okay. So now I have the index into the current frontier where I need to insert. Now what I can do is I will just insert to the current frontier. So I'm going to current frontier of s underscore s of current frontier index underscore s is equal to neighbor. Right? Is this good? Any potential issues? What could go wrong here? So when I allocate this array for the current frontier, the size of this array, I'm going to set it to kind of the maximum possible number of vertices that might be in the frontier, which could be the maximum possible vertices that could be in my graph. So I can put an upper bound on. I can allocate, current frontier to contain possibly all vertices in the graph. That way, I don't have to worry about overflowing the current frontier. But with the shared memory, the private queue, right? The global queue I can allocate as much as I want. With the private queue, I'm limited in shared memory. So it's possible that what happened?
I limit occupants.
It's possible that I overflow, right? You guys see that? Right now, this local queue is built in order to support 2048 integers. It is possible for me to have more than 2048 vertices that I want to enqueue in this thread block. So in this case, I could overflow my local queue. So how can I deal with that? How can I deal with overflow?
Maybe when you reach the maximum occupancy, I mean, you write back to the global queue what you already have, and then you go on.
Right. So one possible thing I could do is once I hit the max, I can go and write everything to the global queue and then continue. But that's going to require me to synchronize across threads because I'm going to need all threads to participate to do that. So I'm going to have to synchronize across threads in the middle of this loop and if statement. And that's not really something I want to do. It's going to be complicated. So what I can simply do, since it's probably not a common case for me to overflow, okay, what I can simply do is I can simply whenever I hit the maximum queue size, I just start sending the rest of the vertices to the global queue. Okay. So basically, when I do an atomic add, all right, what I will do is I will check if I overflow or not. So I'm going to check if the current frontier index is less than the local queue size. If I don't overflow, okay, then I add to the local queue. If I do overflow, then in this case now what I will do is I will restore the local queue size. So I will restore num-current frontier to be equal to local queue size. Okay, and then I will go and add to the global queue. So how do I add to the global queue? Well, it's the same way I did it before. I'm going to increment the global counter, and then add to the global queue. So I will do unsigned int current frontier index is equal to atomic add of the global counter. And then I will use this index to add to the global queue. So right, current frontier of current frontier index is equal to neighbor. Okay. And then of course, now all the thread blocks are going to go. They're going to add to the local queue when the local queue fills up, and now you're going to go to the global. Clear? Any questions about this?
Professor, maybe I missed something. Isn't the maximum shared memory size 1024?
Nope.
Okay.
So the maximum amount of shared memory you can have per thread block depends on the architecture.
Oh, okay. Yeah, true. Forgot.
Okay. Now, depending on the architecture, what you would choose for this value is you would want to be careful to maximize your occupancy. So here, the way I picked 2048 is I observed that I was using 256 threads per block. So if I want to have 2048 threads in total, or 8 blocks, then I want to have, and I can have 96 kilobytes of shared memory. Then I want each thread block not to use more than 12 kilobytes. Okay, so here by picking 2048 and each value is an unsigned int, I'm using 8 kilobytes for the load. Okay, I can increase this more if I want to, and that might improve our performance. But I just prefer to stick to an even power of 2. But I don't have to do that. I can increase this as long as I don't exceed start hurting my occupancy. Okay, so now that we're done, what we want to do is we want to take whatever is in the local queue and send it to the global queue. Okay, we want to take whatever is in the local queue and send it to the global queue. So first, I need to wait for all the threads to finish. So I'm going to have a sync threads over here. And now that I'm done, now each thread block is going to go and it wants to increment the global counter to allocate space for itself in the global queue. So here, the number of elements that the thread block wants to add to the global queue is basically num-current frontiers _x. Okay, so how will we do that? Well, we're gonna we're going to need to have, unsigned int. I want to find where my thread block needs to go and store in the global queue. So I need to increment my global queue counter by the number of local elements that I have. So I'm gonna do I'm gonna name the location the start index. So I'm gonna write current frontier start index. Okay, and that's gonna be equal to atomic add of the num current frontier underscore s. Okay, so the num current frontier is the global counter. And how much do I want to increment the global counter? I want to increment it by the value in the local counter. So I'm going to increment it by num current frontier underscore s. Okay. So atomic increment num current frontier by num current frontier underscore s. So I'm incrementing the global counter by the size of the local queue. Okay, but there's a problem here. What is it? So only one thread in the block should do this, right? The way I wrote it right now, all the threads are going to do the increment, okay? But I can't have that. I only want one thread, just like here with num current frontier equals 0, right? I only want one thread to do it. Same thing here. I only want one thread to increment the global counter, okay? So the way I'm going to do that is as follows. I'm going to write unsigned int current frontier start index, and then I'm going to have an if statement that checks if index.x is equal to 0. And then in this case, I'm going to set the current frontier start index to this value. Okay, clear so far? Any questions? Okay, so now that I've obtained for the thread block where it should store its local queue in the global queue. Okay, part is for thread 0. Only thread 0 has this information. So the next part is for thread 0 to inform all the other threads about the location that it obtained. Okay, and the way we can do that is by simply declaring this in shared memory. So here, what I will do is I will declare this as a shared memory variable. Okay, so that way when the thread index.x increments the global counter, take enough space for the number of elements in the local queue, it's going to store this in a shared memory variable that all the other threads can access later on. Okay, but what does that mean? What do I have to do down here in order for me to make sure that all the other threads can access the right value?
Synchronize?
Right, I'm going to have to do a sync threads so that all the threads wait for thread 0 to allocate space in the global queue. Okay, so now thread 0 has allocated space in the global queue enough for all the elements in my local queue. So now what I want to do is I want to go and store all the elements in my local queue, starting at this index position over here. Okay, now how do I do that? Well, what I'm going to do is I'm going to have thread 0 store element 0 at position current frontier start index. You can have thread 1 store element 1 at the position current frontier start index plus 1. I'm going to have the thread 2 store element 2 at the position current thread index current frontier start index plus 2, etc. So I will have each thread store the corresponding position. So what I will do is I will write if thread index.x is less than num current frontier underscore s, then what I can do is I will write current frontier of the current frontier start index plus thread index.x, okay, is equal to the local current frontier, which is current frontier underscore s of thread index x. Is this clear to everyone? But I still have a problem here. What's the problem? Problems here. How many threads do I have? So I launched this with 256 threads, but I actually have 2048 possible value. Okay. So here, this goes up to 2048, but this goes up to 255. So it's possible that I have more values in my current frontier than the number of threads that I have. Okay, so it's actually not enough for me to use an if statement. What should I do here?
For loop.
Right, I need to have a loop. So I'm going to have thread 0 take element 0, thread 1 take element 1, until thread 255 takes element 255. And then if I have more than 255 elements that I want to increment by 256, and I'm going to have thread 0 take element 256, thread 1 take element 257, thread 2 take element 258, etc. So I will have oops, sorry, I lost my cursor. There it is. So I will write 4 unsigned int. I'm going to call the index that I'm going to store at current frontier index. Underscore s actually. So this is going to be the index into the current frontier that I'm going to load from. Okay, and that's going to start at thread index.x, and that may go up to num current frontiers underscore s. And every iteration I increment it by how much? I increment it by login.x. Okay, so on the first iteration, threads 0 to 55 will store the elements at index 0 to 255. On the second iteration, threads the 0 to 255 will store the ones at 256 to 1023. On the third iteration, we're going to go from 1024 to from 255 from 256 to 511. And then on the third iteration, we'll go from 512 until 512 plus 255. Okay, and now I will use, instead of thread index.x over here, I will use the current frontier index. All right. Is it clear to everyone what we just did? So just to summarize, we created a local frontier. We initialized a counter for it. We initialized the counter to 0. As we were visiting the edges, we were adding the vertices to the current frontier. Once we overflow the current frontier, we started adding the elements to the global frontier. And then when we were done, we had one of the threads in the block reserve space in the global frontier with as many elements as we collected in the local frontier. And then we had the threads collaboratively loop over the elements in the local frontier and store them to the global frontier. Okay? Any questions about this? Okay,
Doctor?
well, yes, question?
Yeah, the code is clear, but I have a question related to the exam. It was an exam question. Yani, the divergence for if thread index.x equals 0, is it how many threads diverge for it? Is it 1 or 31 or 32?
When you reason about divergence, you should reason about it at the warp level. Okay, so when I can't ask how many threads. I should ask how many threads diverge from. So how many threads in a warp, right? So I can ask how many warps diverge, and within a warp, you know how many threads take each branch, diverge to each branch. Okay.
Okay.
So here I'm going to have one of the warps which contains thread index.x equals 0. One of these warps, thread 0 will take one branch, and the other threads will take the other branch. All the other warps are not going to have any divergence.
Okay, thank you.
Okay. Yeah. Okay, so let's start. Oops, do I have a bug? Expression has no which expression. Oh, there we go. So here I wrote current frontier. I should have written plus equals, but looks like my hand slipped, so I just wrote plus. Okay, so current frontier plus equals blockdiv.x. I'm glad the compiler detected that. So we're going to compile, and so remember our performance before was 14.8 milliseconds. So now let's see what performance we get. Okay. So for 14.67 milliseconds. Okay, so we got a fraction of a millisecond performance improvement. So maybe the performance improvement wasn't as impressive as you guys were expecting. And usually this depends on many things. It depends on the graph. It depends on it also depends on the hardware, because some architectures have, the later architectures have excellent atomic operation support, whereas the earlier ones didn't. So in the previous architectures, this was a kind of a stronger optimization. But here, for this particular graph on this particular architecture, the performance improvement we got from privatization was small, but you may expect it to be larger on other graphs or in other architectures. Okay? Any questions about privatization? Yes.
Just about the algorithm, is there a way to write an algorithm that that syncs with the CPU, and you follow the path of the graph?
So there are ways to synchronize with the CPU during using atomic operations, but that's an advanced topic that's not very relevant to today's material. Okay. All right, so having seen this, let's go back. So here, this is the code that we wrote. This is the continuation of it. So minimizing launch overhead. So one thing that we've been doing so far is we've been calling a kernel for every level, right? And the reason we're doing that is because we need to synchronize across all the threads on each iteration. Now, when we went to this frontier-based approach, and in the approach we had before, we were launching a thread for every vertex on every level, and usually we have not many vertices, so we have many thread blocks. Whereas when we went to this frontier-based approach, we're only launching a thread for every vertex in our frontier. And what that means is that the number of vertices in my frontier may be small enough to require only one thread block to process. Okay, and this presents an opportunity for optimization. So we've seen that we need to synchronize between levels because we need to wait for all threads to enqueue all the vertices of the current level before proceeding to the next level. And so far, what we've been doing to synchronize between levels is we've launched a new grid for each level. And the overhead of launching a new grid is because we have the overhead of doing the actual launch, and then we also have, remember how we were copying this counter in order for us to figure out whether we are done or not. Now, if it happens to be the case that consecutive levels have few enough vertices so that these vertices can be executed by one thread block, then what we could do is we can execute multiple levels in a single thread block and synchronize between them using sync threads. And what this does is that it reduces the total number of grid launches that we need to make. Okay, so if I show you a picture, if over here at level 0, I just have one thread block. Usually, by the way, this is at the beginning and at the end. Okay, so usually the levels that are at the beginning are usually small because it takes a while for me to kind of have a big enough frontier so that I start touching many vertices every iteration. And usually the levels at the end are also small because that's just the nodes that are very far away from the source vertex. So it takes a while for me to kind of catch all these very distant nodes. So usually the levels at the beginning and levels at the end have few vertices. Okay. So what I can do is if in between two levels, the number of vertices that I have in the frontier is small enough such that it can be processed by a single thread block, what I can do is rather than launching a grid for level 0 and a grid for level 1 over here, or down here, rather than launching a grid for level 5 and then a separate grid for level 6, what I can do is I can just have one thread block process both level 0 and level 1 and use a sync threads to synchronize between them. And similarly, I can have one thread block process level 5 and level 6 and do a sync threads between them. So consecutive levels that have a small enough number of vertices, we can synchronize between these levels using sync threads rather than having to call a kernel every time. Okay, is this optimization clear to everyone? Okay, so let's see the impact of this optimization. So I'm going to, I've already implemented it. I call it level sync. And I'm going to compile it. Okay, I'm not going to show you the code. I'm going to leave that for you as an exercise, but I'm going to compile it just to kind of show you what we can get, the amount of improvement we can get by doing an optimization like this. We're going to run, and as you can see, we've also have a reduction in the execution time because we've saved on some of the kernel launch. Okay, let me run again, see if I get anything better. Okay, so as you can see, we also get some improvement in the performance. Okay.
Hi, Professor.
Any questions about this?
Yeah, Professor.
Yes.
I was wondering, how do you go about knowing when to launch like a single block grid or when to not launch it? Like, is it a heuristic?
So what you will need to do is you will need to check the number of vertices in your current level. Okay. And if the number of vertices in your current level is less than the number of vertices that you can process in a single thread block, then what you can do is you can have that thread block do everything so that it generates the next queue. If you find that the next queue also has enough vertices that can be processed in a single thread block, then in that case you can just do a sync threads and go ahead and process that next level. Okay, so the way you find out is if your current level, if your previous frontier has fewer vertices than what can be done in a block, and your next frontier also has fewer vertices than what can be done in a single block. Have I answered your question?
Yes, certainly. Thank you.
Yeah, you're welcome. Any other questions? Okay, so ends our today's lecture. You can read more about what we covered today in chapter 12 of the textbook. Does anyone have any final questions before we conclude?
Yes, can we add multiple levels, like not just one level?
What do you mean? Are you mean here?
Yeah.
Yes, of course. I mean, you as long as your next frontier, your previous frontier and your next frontier are fit within a block, you can go on for multiple levels.
Okay. Yeah. Thank you.
Yeah, you're welcome.
Professor, would in this case, the first example you gave for level 0, for example, it's kind of like thread coarsening. If you apply it to all the levels at the same time, does it help or no?
It's a little bit different from thread coarsening. Here, I'm reusing a thread for something else, but I'm not reusing it for something else that was meant to execute in parallel with it. Okay, I'm reusing it for something else that was going to execute after it. Okay, so it's a little bit different from thread coarsening. But can you repeat your question?
If you do, for example, kind of this execution pattern for all levels at the same time, would it help or not really?
What do you mean do it for all levels at the same time?
So,
we
so
need to
for
wait
example,
until we finish to execute the next one.
no, I mean, for example, in level 3, there are some blocks where you could merge them together.
Oh, I see.
Between.
Yes, I see. That's excellent. Excellent observation. So I think what you're saying is, so maybe here I have 256 threads, and I have 256 vertices in my level, and maybe here in the next level I have maybe 270 vertices. So maybe it's better for me to do thread coarsening to use the 256 threads to do to process the 270 vertices, as opposed to having to create 2 blocks and pay the price of having to have a new grid launch. Is that what you mean? So maybe it's better for me to between level 1 and level 2. Maybe it's better for me to use 1 thread block to do the work of these 2 thread blocks, rather than using 2 thread blocks. And if I use 1 thread block to do the work of the 2 thread blocks, then I can sync threads between them rather than launching a new grid.
Kind of, that's what I meant, yani.
Yeah, it's possible. I mean, it's possible. It's worth a try. Again, you're losing parallelism, but you're saving on the sync on the grid launch overhead, and it just has to do with how expensive is the grid launch compared to the workload of these 2 blocks. Okay, so that's something that one would have to experiment with and see which one has higher overhead. Okay, so thank you for that question. It's a good observation. Any final questions? Okay, if there are no final questions, then that's all for today, and I'll see you next time. Bye, everyone.